So if you're, knee-deep in a project, maybe you're getting ready for a huge code refactor, or you're just trying to figure out why a function that worked perfectly yesterday is suddenly failing today, you know the risk. Every single time you touch a line of code, you introduce this possibility of disaster somewhere else.
Right.
Welcome back to the deep dive. We took your sources, your research, and your notes, and we are cutting straight to the solution. Today, we are deep diving into unit testing. It's the essential shortcut to reliable, trustworthy code.
That's absolutely right. We are moving you past that chaotic cycle of manual quality assurance. Our mission here is to extract the definitive principles and the tools for validating that the smallest, most granular components of your application—
The units.
Exactly, the units, that they function flawlessly, independently, and consistently. This is really about building confidence from the ground up.
And I think we all share a memory of the pain points that make this deep dive so necessary. I mean, our sources laid out that classic programmer nightmare.
Yeah.
You execute the entire program by hand, you click through a dozen menus, and then finally you find a bug. Then you have to spend hours manually documenting the error, taking screenshots, writing up all the steps to reproduce it.
And that's where the chaos really begins, isn't it? The problem isn't just the time you spend documenting, it's the sheer difficulty of making sure your fix actually works and, more importantly, stays fixed.
Right.
You solve it on your machine, but when it goes to the shared environment, does the error just reappear? This whole manual process is slow, it's expensive, and it is just not repeatable. We need a system that fixes this reproducibility crisis that's kind of inherent in software development.
Okay, so let's jump right into that solution. When we talk about unit testing, it sounds like a lot of technical jargon, but the concept is actually, beautifully simple.
It is.
It's a technique where individual units or components are tested in isolation.
And defining that unit is so crucial. It is the smallest testable piece of your code. Think of it like a single function or maybe a specific method inside a class or even a small module. The power is in the focus.
So you're not testing the whole app.
No, not at all. You are just ensuring this one specific thing does exactly what you wrote it to do. If it's supposed to add 2 numbers, you test only the addition. If it's supposed to format a date, you only test the formatting logic. The singular goal is validation.
Okay, so what separates just a casual test from like a world-class industrial strength unit test? Our sources didn't just define it, they gave us a pretty rigorous checklist. We found 5 essential characteristics that really transform this practice into a strategic superpower for developers. And the first, and I'd say arguably the most important, is isolation.
Isolation is the bedrock. It really is. It means your test focuses only on the functionality of that one unit, and critically, it has to be independent of every other part of the system.
Right.
If your function calls another component, or worse, it relies on an external factor like a database or a network API. That's where true isolation gets tricky.
That brings up a really important question because, in the real world, units are almost never islands. If I have a function that's supposed to get customer data before it calculates their loyalty points, how do I actually test the calculation isolated from the slow, maybe unreliable database connection it needs?
That's a fantastic question.
So doesn't the testing environment have to perfectly mimic the production environment?
That's the challenge, and it's where more advanced unit testing concepts come in. You solve this using techniques called mocking or stubbing.
Okay.
So instead of letting your function call the real, slow, external database, you substitute it with a mock object. This mock is basically a dummy version that you program to reliably return exactly the data you need for your test.
So you're faking the database call.
You're faking it, exactly. This ensures that when the test runs, you are purely evaluating the calculation logic. It eliminates all those external variables, and you truly achieve isolation.
And that makes the whole process fast and predictable, which brings us perfectly to characteristic number 2, automation. This is the key strategic shift away from that painful manual slog we were just talking about.
Absolutely. Unit tests must be automated. They have to be. It allows them to be run constantly and consistently. Our sources really highlighted that this automation is usually integrated into a continuous integration or CI process.
We've mentioned CI a few times before, so let's be specific for the listener. What does continuous integration actually mean for the average developer who's using unit tests?
In short, CI is your automated quality gate. It means that every time a developer commits new code or proposes a change, the CI system automatically pulls that code and runs the entire test suite.
The whole thing.
The whole thing, often hundreds or even thousands of unit tests, before that change can be merged into the main code base. If even one test fails, the merge is rejected.
Oh.
This gives you immediate, non-negotiable feedback, and it prevents bad code from ever contaminating the main project.
Preventing contamination, ensuring consistency. That leads us right to the third essential characteristic, repeatability. I really can't stress this one enough.
Repeatability is non-negotiable. It separates serious engineering from just guesswork. A unit test must produce the exact same result every single time it is run, period.
Every time.
Whether you run it on your laptop, the automated CI server, or a year from now, if the input is the same, the output must be the same. If a test fails intermittently, we call that a flaky test, and its value is 0. You just can't trust the result.
And we need that feedback fast, which is number 4, fast execution.
If the tests are slow, developers won't use them. It's that simple. If running the test takes an hour, a developer might run them once a day. If they run in seconds,
They'll run them constantly.
dozens of times an hour. Unit tests, specifically because of that principle of isolation where you're not waiting on networks or databases, they're designed to deliver that rapid feedback, ensuring the development flow isn't interrupted.
And finally, we get to number 5, which sort of ties all of these concepts together strategically. Code coverage.
Coverage is really the measure of trust you can put into your system. The aim is to cover as much of your code base as possible. Every single decision point, every loop, every possible path the code can take. This means not just testing the happy path, the expected input, but strategically targeting edge cases.
What kind of edge cases are we talking about?
Well, think about the boundaries. If your function accepts ages, you should test 0, test negative numbers, test extremely large numbers. If it accepts a string, test an empty string or a string with, I don't know, non-standard characters.
Right.
Good unit testing isn't just about proving the code works, it's about proving how hard it is to break. High coverage gives you the confidence to do things like major refactoring. You can restructure the internal code, run your tests, and if they all pass, you know with certainty that the external behavior hasn't changed. That is the strategic payoff.
That shift from, defensive coding to confident refactoring is huge. Okay, that sets the foundation for what good unit testing is. Now let's talk implementation. Our sources pointed us towards the Python ecosystem, and specifically how developers move from basic built-in checks to professional frameworks.
Right. We often start with a built-in assert statement for immediate checks, especially with functions that return a value, what the source calls fruitful functions. The basic mechanism is just a true-false check. If the condition after assert is false, the program just halts with an assertion error.
So you get immediate, explicit failure notification.
Exactly. But when you start managing hundreds or even thousands of these simple checks, just relying on individual assert statements scattered all over your code becomes completely unsustainable. That's where you need structure, scalability, and, most importantly, robust reporting.
This is where a framework comes in.
Precisely. You move to a dedicated framework, and for Python, the professional standard is typically pytest. It's far more than just a replacement for assert. PyTest fundamentally changes how you organize, run, and interpret your tests.
So if I'm running a huge suite of tests, what does PyTest give me that simple assertions just miss?
Well, first, it's an orchestrator. It automatically discovers all your test functions, even ones buried deep in various folders, just by following simple naming conventions. Second, the reporting is transformative.
How so?
Instead of just halting on the first failure, it runs the entire suite and gives you a clean, summarized report. It details exactly which tests failed, where they failed, and importantly, it provides detailed information about why the assertion failed, showing you the actual output versus the expected output.
So it manages the execution and gives me the full postmortem analysis.
And it enables advanced testing patterns. For example, PyTest lets you define something called fixtures.
Fixtures.
Fixtures are reusable functions that set up a known baseline environment for your tests. Say you need to test 10 different functions that all need a clean list of 50 customer IDs. Instead of writing that setup code 10 times, you define one PyTest fixture that handles the setup and teardown. It promotes clean, DRY, do not repeat yourself code in your test suite.
Okay, that makes sense.
It also supports parameterization, which lets you write a single test function but feed it 10 different combinations of inputs, like those edge cases we mentioned, dramatically reducing code duplication.
That capability for setup and streamlined edge case testing really elevates it from a basic tool to more of a system management layer. Now let's make this concrete. Let's look at the practical examples from your sources which show the sheer variety of components we need to test.
Right, we saw some simple examples like exercise 1, just testing subtraction, which shows the absolute necessity of testing foundational math, but the concepts scale up quickly. Take exercise 2, converting seconds into the HHMSS format.
And that test isn't just about math, it's about a rigid adherence to the output structure.
Precisely. You're testing the logic for converting, say, 4,150 seconds to 01.09.0 nome, but you're also validating the formatting, the leading zeros, the colons. If this function is feeding data to a UI or a logging system that expects that exact format, that unit test becomes critical. It's testing presentation logic, but in isolation.
Okay, now we get to the really illustrative examples, exercises 3 and 4, because they introduce dependency, which ties all the way back to our core principle of isolation. Exercise 3 involves calculating the hypotenuse of a right triangle.
So the hypotenuse calculation is a complex mathematical unit. When you test it and you ensure its correctness across all kinds of inputs, positive legs, zero legs, you now have a high confidence building block. You can trust that unit.
And exercise 4 shows us why that transference of trust matters so much. The assignment asks you to first define and test a function called slope, by 1, y1, by 2, y2. Once that's done, you define a second function, intercept, which actually calls the already tested slope function.
This is the perfect practical demonstration of why isolation is so strategic. If you rigorously tested slope, you covered all its paths, including that crucial edge case where the slope is undefined, a vertical line, you gain massive confidence.
Okay.
Now, when you test intercept and that test fails, you know the probability is near zero that the failure is inside the slope function. The problem is isolated to the new logic you just wrote within intercept.
It gives you a surgically precise way to debug. Instead of looking at 1,000 lines of code, you're looking at maybe 10.
It accelerates development, it manages technical debt, and it allows for safe refactoring because you have verified contracts, your tests around every single piece of functionality.
So what does this all mean for you as you dive back into your code base? We've covered a tremendous amount of detail, but I think the ultimate strategic takeaway is this. Unit testing is not just a bug-finding tool. It is a developer's assurance policy.
Well said.
It's the shift from manually trying to chase down intermittent errors to having immediate automated certainty about the function of your code.
And to solidify that shift, let's just quickly review those 5 essential aspects that define mastery in unit testing. Remember isolation, which requires using tools like mocks to truly separate your unit. Automation, running tests frequently through systems like CI. Repeatability, ensuring identical results every time.
Every single time.
Fast execution for rapid feedback, and excellent code coverage, especially focusing on those difficult edge cases.
That's a comprehensive checklist for reliability.
And this raises one final provocative question for you to consider as you implement these tools. Think back to those dependent slope and intercept functions. We talked about how testing a small unit like slope transfers confidence to a larger system like intercept. How high does your unit test coverage need to be to give you near absolute confidence in the entire complex application? And conversely, if that foundational unit, slope, only has 50% coverage and you missed a critical edge case, what is the cascading impact of that single untested path across a massive software project?
The lesson being, the weakest link determines the reliability of the entire chain.
Exactly. Mastering unit testing means mastering that cascading impact, understanding the exponential growth of trust that comes from full coverage on your foundational units. That is the true strategic value of this discipline.
A profound thought to leave with. Thank you for joining us for this deep dive. We hope you feel well equipped and ready to start building that bedrock of confidence in your code today.